This is the last hour of Physics 1B. We have about 35 minutes or so left. 30 minutes left, right? We finish at 12:50, I think, in this class. So, yeah, let's get going. The next topic we want to discuss, which is related to what we just talked about, is Pascal's law. I always heard of it as Pascal's Principle. I don't know that it really matters what you call it. It's the idea that matters. Now, Pascal's principle is related to what we just talked about because they are pretty much the same idea. So let's write it down again. We just learned about variation of pressure with depth, and that is P naught plus rho GH. The pressure at the top of the fluid plus rho GH is equal to the pressure at the bottom of the fluid. So I want you to think about the following scenario then. Suppose that I have a container, and again, this container is going to be filled with, well, I was going to say we could fill it with air. Let's fill it with air this time. So let's say we have a container that's filled with air, and it's sealed off at the top, so it's filled with air here, right? But now let's add one thing. Let's say that there is a movable piston on the top right here, okay? There's a little piston that we can move up and down. So it's sealed here and here, all sides, right? So that the air can't escape, but we have a piston here at the top. So what Pascal's law talks about is what happens to the pressure, let's say at this point right here, where we know at this point that if we can calculate the height from this point to this point, we can find what the pressure is here by using that equation, right? But what would happen if we were to push down on this piston with some kind of force? What would change? Well, normally the pressure at the top of the fluid is just atmospheric pressure, okay? If we were to exert a force on top of this, that would increase the force on the surface, right? Would everyone agree? If I push down with the force on top right here, then the pressure on the top up here is going to go up. The pressure on the top of the fluid is going to increase, right? Do you all agree? If I push down, pressure goes up, okay? So what's going to happen to the pressure at the bottom? It has to go up too, right? You know, if I push down with the pressure on top, with a force, let's say that creates a pressure of, let's say, 0.1 atmospheres, okay? So let's say I push down with the force, and it adds 0.1 atmospheres to the pressure at the top, okay? So now the pressure at the top is no longer P naught, it's 1.1 atmospheres, right? Well, isn't the pressure at the bottom just going to increase by the same amount? Right? Doesn't that make sense? That if I add a little bit of pressure at the top, well, look at your equation. All it says is pressure at the top, right, plus rho GH. So if I increase the pressure at the top, the pressure at the bottom is going to increase by exactly the same amount. Not by some fraction of it, but by exactly the same amount. That's what Pascal's law says. It says, the pressure applied to an enclosed fluid is transmitted undiminished to every portion of the fluid and the walls of the containing vessel. Put in a short way, when I push down on the top of this system, it's going to increase the pressure everywhere by the same amount that I push down on it. It's really contained directly within this variation of pressure with depth equation. You could say that these two basically say the same thing. This is a mathematical statement, this is a conceptual statement on the left. Right? Does that make sense? So what that means is that, yeah, when you apply pressure, you add that same pressure everywhere inside the system, okay? Every piece of the system feels that same pressure. And this law is nowadays used to explain why things like hydraulic lifts work. Hydraulic lift is something that uses fluids to help you to lift an object up with a minimal amount of force, okay? And this is a really simplified example of what a hydraulic lift does, okay? So in this system, what we have are two movable pistons, one right here and one right here. The red, I don't know what you want to call this color, tan. This is a fluid. All inside of here is a fluid, okay? And sitting on top of the piston on the right, which has, you'll notice, a really big area. Now this is like a two-dimensional thing, but you're supposed to imagine that this is like a, you know, it's like a cylinder or a square, like a cube or something that's being pushed up. Same thing over here, where the area of this cylinder is bigger than the area of this cylinder, okay? And the idea here is that we're going to push down on this side where there's a very tiny area, and we're going to use the force that we push down over here to try to help us push a car up. Okay? And the only way that this can work is if the area on the left is smaller than the area on the right, because something interesting will happen if we do that. And this is similar to the way that a thumbtack works that we talked about earlier. So if the pressure applied, right, to an enclosed fluid is transmitted undiminished to every portion of the fluid, right, then if I push down on the left side over here with some pressure, and the pressure that I push down on it with is equal to that force F1 divided by area 1, right, because pressure is force divided by area. If I add this much pressure to the system, then that pressure has to be transmitted through the fluid, almost like magically, from over here all the way to over here, because I add pressure here, it has to increase the pressure over here too, right? So that means the amount of pressure that's going to be felt on this piston over here should be equal to the amount of pressure that I apply. And that's what Pascal's law says, is that these two pressures are going to be equal to each other. This is the added pressure, and that pressure has to basically be felt all throughout the system. So on the right-hand side, you should feel the same pressure. Okay. So how does this end up working, or why does it work? Well, if we look at what happens if I rearrange the equation the following way. I'm going to multiply a to the left-hand side. I'm going to put these things in parentheses here. We'll multiply by F1. We get this really nice relationship here that you can exploit to gain what's called a mechanical advantage. And that means you can use this to basically lift objects that are way too heavy for you to normally lift by designing a system like this. Because, let's say if A2 is equal to, let's say it's 5 times as big as A1, okay? Let's say the area on the right-hand side is 5 times as big as the area on the left-hand side, right? Then what would the ratio of A2 over A1 be? Well, the ratio of A2 over A1 would be 5, obviously, right? So using that simple example, this is the result that we get, and let's talk about what it means. 5 times F1 is equal to F2. Now notice F2 ends up being the force that gets applied to this piston over here, right? So that means that the force that's felt by the car, so think about this, the force that's felt by the car, F2, basically force on car, is, what is it? It's 5 times as big as the force over here. So let's take a normal weight for a car. What's a normal weight for a car? Let's say a car weighs 1,000 pounds. Let's say a car weighs 1,000 pounds, okay? How big of a force would you need to push with to lift a car that's 1,000 pounds, according to this? How big would F1 need to be if F2 is 1,000 pounds? We're not using SI units here because it doesn't matter, because it's a ratio. It just doesn't matter. We can use this. 200 pounds of force. Well, that's an interesting number, because I weigh more than 200 pounds. That means that what I could do in a system like this, okay, is I could literally stand on top of the piston on the left, right? And the car would lift up just on my own weight. Does that make sense? And does it make sense why that's really powerful? The ability to lift heavy objects, right, with very minimal amounts of force, really powerful. If you have anyone have a hydraulic jack in the back of their car that they've used to, this is exactly like pulleys, Kevin. That's exactly right. Pulleys provide a mechanical advantage by just taking multiple pulleys, right? If you use 2 pulleys, then you get half the force needed to lift the same object. If you use like 4 pulleys, it's like 1/16 the force you need to lift the object, right? It's exactly like pulleys. And the phrase that people use is mechanical advantage. You gain a mechanical advantage by using a system like this. Now notice there is something that you're losing in this process, right? What do you notice is happening on the left and right-hand side right here with these distances? It looks like the distance delta x1 is significantly bigger than delta x2. Do you all notice that? So it looks like if I push down on the left by a large distance, the car is only going to go up a short distance, right? You all see that? And that's because otherwise you would be getting work for free, okay? Remember that work is force times distance, right? Let's just have a little trip down memory lane. Work is equal to force times distance, right? Force times displacement, really. It's really F dot delta x, right? It's like F times delta x times the cosine of an angle, but all the angles here are 0, so it doesn't really matter. So you can't get work for free. So in this particular case, if the system had no friction and there were no losses due to anything else, then we could say that basically F1 times delta x1, that would be the work that you do to push the car up, should be equal to the work that's done on the car, in this case, which would be F2 times delta x2. But we know F2 is like 10,000, F1 is like 2,000. So in order for this to work, delta x2 has to be much smaller, right? Delta x2 has to be less than delta x1. In this case, if we push down by a distance of 5 meters, can anyone guess if we're using these numbers? If we go down by 5 meters, how far do you think the car is going to go up? So if I push this down 5 meters, how far do you think the car will go up? If you're just going to guess. 1 meter, about 1 meter, exactly, 1 meter. All the ratios are all going to be the same. It's always going to be 1 to 5, right? So you do lose something, but you know the way that these systems often work is you can just keep pumping, and they'll design things so that like you push something down like a little bit, the car goes up a little bit. You push it down again, the car goes up a little bit. You push it down again, the car goes up a little bit. I think that's how a lot of those hydraulic jacks work in cars. I've never used one. All the jacks in my cars have always been like that. But if you go to an auto shop, they're going to have a hydraulic lift that they use to lift the cars up, right? Do we have enough time to do this problem? We do. Okay, do you all feel like you have a somewhat of an introductory understanding of what Pascal's law says and how it would apply to a system like this hydraulic press right here? And does anyone have any questions or comments? Oops. Okay. So, let's do an example problem. By the way, I don't know if how important this is to you all, but I take example problems from your textbook, but I also take them from other textbooks as well, and that's why you might not be able to find this problem in your textbook. All your textbook does with this particular topic is they just introduce it, and then they show a picture, and then they just move on. They don't do any problems. But then in your homework, you're going to have problems that actually ask you to use this idea. And so I feel like if you haven't, I don't even think there's any equations in the book for this. I don't know. Anyway, regardless, let's try to solve this problem here. And let's use this picture. Okay. So it says, in a car lift used in a service station, compressed air exerts a force on a small piston that has a circular cross-section and a radius of 5 centimeters. Okay, so we have a small piston. We're going to say that's this one here. It's got a radius. We'll call it R1. And we're going to say that R1 is, 5 cm. Okay, that's the radius of this piston over here. The pressure is transmitted by liquid to a piston that has a radius of 15 centimeters. So that's going to be the radius of this one here. We'll call that one R2. R2 is 15 centimeters. Now notice, these are radii, they are not areas. If the ratio of the radii is 3 to 1, see if you all can tell me before we do it. If the radius of this is 15 and the radius is 5, so that the ratio is 3 to 1, right? 15 to 5, 3 to 1. What's the ratio of the areas going to be? Nope, it's not 3 to 1. It's 9 to 1. That's exactly right, 9 to 1. Because area is like pi r squared. So if you take r2 squared over r1 squared, 15 over 5 squared is 3 squared, which is 9 to 1. Exactly. Okay. So that means that we should get a 9 times effect in the force, right? Let's see if we do. The question is, what force must the compressed air exert to lift a car weighing 13,300 newtons. Wait, isn't the answer 13,003? Yeah. There's two questions. That's good. The way this question's asked, I've never noticed this before, but isn't the answer... It says, what force must the compressed air exert to lift a car weighing 13,300 newtons? Isn't the answer 13,300 newtons? Oh, I think I misunderstood. Oh, I see. Okay, I misunderstood. The compressed air. I'm sorry to confuse you. I'm not trying to confuse you. Hey, click. Oh no, it's doing that thing where it won't let me click things. Can I Control-Z it away? Alright. It says, compressed air exerts a force on a small piston. So, the answer to this part, what force must the compressed air... This is F1 in our picture. That's what they're asking for, is F1. Okay. And then the question is, what air pressure produces this force? So we want to find the force F1, and we want to find the pressure inside of this area. The whole pressure in here is what we want to find. Is it... The way that these things are asked sometimes is super confusing. What air pressure produces this force? Okay, so let's go through this. So what we know is the pressure inside here has to be increased by the same amount due to this force that we're applying here. So we can use the same relationship that we just wrote down a second ago, which is that the force 1 divided by A1 has to be equal to force 2 divided by A2. And we can rearrange this to solve for F1. So F1 in this case should be equal to F2 times the ratio of A1 over A2. And now we can just plug the F2 in here. So the car weighs this much. I should have made it very clear right here. The weight of the car is what our F2 is, 13,300. Because after all, if I want to lift a car that has a weight of if the weight of the car here is 13,300 newtons, the minimum force I need to exert to lift the car is equal to that force, right? So, plugging everything in here. We plug in A1. So remember that the way areas are calculated, if it's a circle, it says it's a circular cross-section. So we know that A1 is going to be pi times R1 squared, and A2 is going to be pi times R2 squared. We can plug these into our equation up here. So we're going to have pi R1 squared over pi R2 squared, which means that F1 is going to be equal to 13,300 newtons multiplied by the ratio of R1 over R2. They're both squared, so we can just put the squared up like this, and then we can plug in their values. So R1 is 5 cm, and R2 is 15 cm. Normally you need to convert everything into meters, but in this case, because there's a ratio, the centimeters will cancel out. If I converted this to meters, the ratio wouldn't change, right? I'd have 0.05 over 0.15, which is the same as 5 over 15. So there's no need to convert in this case, because the units will cancel here and here. And so our answer then is going to be whatever this is divided by 9. We didn't even need to really do the problem, right? We knew what the answer was going to be. We knew that it was going to be a 1 to 9 ratio because we figured that out right at the very beginning, right? It's the power of being able to use ratios. We don't even really have to do anything in this problem if you have a good, sound, fundamental understanding, conceptual understanding of the way that Pascal's principle works. So you can lift a car with a weight of 13,300 newtons with a force of about 1,500 newtons. That's the idea of what the problem says basically here. Okay, does anyone have any questions? The last part of this says, what air pressure produces this force? So if you look at really carefully at what they're saying, it says, in a car lift used in a service station, compressed air exerts a force on a small piston. I think the idea here is that you're shooting compressed air in this direction, right, in order to make this happen. And I think in the second part, what air pressure produces this force? I think what you have to do is to go back to our definition of pressure is equal to force over area. And just use F1 and A1 in this case. So we would use F1, which is 1478. Is something blocked? Ah, I'm so sorry. Yeah. Here, if I zoom out just a little bit, I think that should fix it. Is that okay now? Sorry about that, I forgot. I made the Discord chat really big because I wanted people to be able to read it. People said they couldn't read it. I'm going to have to make it a little bit smaller, I think. It's taken up a little bit too much space over there. Okay, but thank you for noting that it was blocking, because I'm not always going to notice that. All I see is just the whiteboard stuff. I have the Discord, I have OBS on the opposite screen, but it's pretty far away and I can't really see it. 1478 divided by the area. The area is going to be pi times r1 squared. R1 is 15 centimeters. Okay, now we need to convert, I think. Am I right or am I wrong? Do I need to convert now? We have to convert it, right? Because newtons has meters inside of it, yeah? So we have to convert. All right, what do we get? We do this. Yep, not a ratio, exactly. And so I got a pressure of, excuse me, 188,000 pascals. I'm just going to round it out to 188,000 pascals. That is the pressure that you'd have to exert. So it looks like it's about, about 90% more than air pressure. Can I check something real quick? Yeah, it's 12:50, right? So we have 9 more minutes. 9 whole minutes to cover something. We can probably introduce you to Archimedes Principle, which I believe is what's next. Buoyancy, Archimedes Principle. Yeah, that's what's next. I think in 9 minutes, I might be able to at least derive the way that it works. Let's see. Let's see if I can do it. And if we don't finish it, then we'll just finish it up next week. By the way, we don't have class Monday, in case you don't know, because of Labor Day. I really wish they would start school the week after Labor Day. But it's nice having a day off. It's always so distracting to miss a class in the first week. It just kind of throws things off. And, anyway, no big deal. We get through it. So buoyancy. How do we talk about buoyancy? Well, again, we can kind of do something we did earlier. In fact, I don't want to do it because it gets confusing to me. So let us again start with the same thing we've started with for most of these problems. You start off with a beaker full of water. This time we're going to put something inside of it. Okay, so we again have a beaker full of water. And now what we're going to do is we're going to imagine that we have placed like a piece of wood, like a column of wood. We're going to imagine we put a column of wood inside of here, okay? So we put like a stick or something inside of this water. And we're going to fully submerge it, because when it's fully submerged is kind of the simplest scenario. Let's make it a different color. So we're going to place inside of here a column of wood. Connect it up, make it all three-dimensional like. This proof goes very similar to the other one, so we can get through it hopefully pretty quick here. Okay. So now I have an actual object that's placed into the water, okay? We put a piece of wood into the water, right? We submerge it into the water, okay? We're going to leave it submerged inside the water, right? And we're just going to identify what the forces that are acting on it are, all right? Now, you all know that if you take a piece of wood and you put it in water, that it's going to float, right? And that in order to submerge a piece of wood, you have to hold it under the water. Would everyone agree with that statement? The wood is just going to float up, right, over time? So to actually get it to stay under the water, we would have to hold it there, right? But don't worry about that. We're just going to say we push the wood down into the water. We're going to freeze time before the wood floats up, and we're just going to think about the forces that are acting on it, okay? Now, because you know the wood floats up, would you all agree that that has to be because of a force? It has to be a force that pushes it up, because normally things go down, right? Weight pulls things down. So there must be some kind of a force acting on this block, this piece of wood, that pushes it up, and we call that the buoyant force, okay? Now, let's label the forces that are acting on our object. So we are going to have a weight that pulls down like this. Make it green. And let's make it short. We're going to have a weight that pulls down like this. And then in addition to that, we're going to have something called the buoyant force, okay? And our goal is to calculate what the buoyant force is. How do we actually define it, and what is it? In this case, I would assume that this buoyant force, which I'm going to use the symbol B for, this buoyant force is probably greater than the weight. If the object is wood, the buoyant force is greater than the weight. We know that. But what's the value of the buoyant force? Well, it turns out that the buoyant force comes purely from the difference in pressure at the bottom versus the pressure at the top. As we said before, if we call the pressure down here P2, and we call the pressure up here P1, we know that they're different from each other now. In fact, we have a relationship that says that P2 is equal to P1 plus rho times g times h, assuming that h is the height of this object. Let's also throw in here an area, so the top thing has an area A, the bottom thing has an area A, right? And the buoyant force now has to come from the difference in pressure at the bottom and the pressure at the top, right? So let's draw a couple more lines on here. So as we know, that buoyant force, right? I'll leave it on there. Has to come from the pressure on the top and the pressure on the bottom, the fact that we know the pressure on the bottom is bigger than the pressure on the top, and that means because the pressure on the bottom is bigger, the force on the bottom is bigger, and as a result, there's going to be an upward buoyant force acting on this object, right? So what we can do is we can just say that the pressure on the bottom, that's exactly right, I think, Troy. I think that's exactly right. So the pressure on the bottom creates a force on the bottom, which is equal to P2 times A, right? So there's a force down here, which is P2A. There's also a force on the top, which is P1A, okay? And now that I've written them like this, I'm going to get rid of this buoyant force right here for just a second, because I don't want to have too many forces acting on my object. Okay? So we've got P2A down here, which is a force. We've got P1A up here, which is a force. And we know that the difference between those two, P2A minus P1A, this is the only place the buoyant force could come from. So we're basically just going to say that this is the buoyant force. Now, what are these equal to? Well, we know P2 minus P1. We know what it's equal to from this equation, right? It's rho GH. So on the left-hand side, we can just put rho GH times A, and that should be the buoyant force. But hey, you know what? What's H times A? What is H times A? It's the height of the column times A, right? So it's V, it's volume, exactly. So we can write this as rho times volume times G is equal to the buoyant force. And that is how the buoyant force would be defined in this case. This is for full submersion. Now, what are the quantities that show up in this system? V is the volume of the object, okay? And you know what G and rho are, right? Rho is the density of, not the object, but the fluid, right? And then G is just gravity. So maybe a better way to write this that could be more clear is that the buoyant force for fully submersion, it's only as true when it's fully underwater, okay, would be equal to the density of the fluid, I'm going to write that as rho F, times the volume of the object, I'm going to write that as V sub O, multiplied by G. I think this is probably a little bit clearer way of defining this. So that is what, oh boy, thank you so much. I will move this over here. There we go. That might be a better way to define it. The density of the fluid times the volume of the object times G. All right. And I apologize, I'm going to scroll up for just a second to go find something to click over here. This is stated in something called Archimedes Principle. Archimedes Principle applies to more systems, but this is what it states. It says, when a body is completely or partially immersed in a fluid, the fluid exerts an upward force on the body equal to the weight of the fluid displaced by the body. The weight of the fluid displaced by the body. Now, if the object is completely underwater, the amount of fluid displaced is going to be equal to the volume of the object itself. When the object is halfway submerged, it's only going to be the portion that's underneath the water. Now we're out of time, so we'll go into more detail about this next time, but, you know, read up on Archimedes Principle, and a week, we're not going to meet for a week, by the way. A week from now, we'll come back and we'll talk more about this, okay? So that's all for today. I'm going to stop the recording. If anybody has any questions, I will stick around for a little bit. I don't have much time between this class and my next class, so I can't stick around too long. I do need a break, and I have to go send some emails and do things like that. But I'll stick around for 5 minutes or so. Those of you that need to get your ad codes going, we'll do that right now. Everyone have a good time. When can we view today's lecture online? Well, you just did it, but you'll have the opportunity to look at it again later whenever I post it to YouTube, and I'll get that done when I get it done. I'll try to get it done soon. Yep, everyone have a nice day. Thanks for coming today. Hope you all have a nice weekend. When will the homework be due? What are you talking about? There's a due date on Mastering Physics. Is that what you're talking about? Del said? The due dates are on Mastering Physics, yeah. Can you not see the due dates when you go there?